It can hold up on a hard throw. It's slippery through the air and really optimizes lift to drag in a way that none of the other airplanes could. How is this flying toy connected to smarter car design, golf balls, or clean energy? By unlocking the principles of flight and aerodynamics, we could affect the world on a massive scale. There are two key adjustments that will help any paper airplane fly better. The first one is called dihedral angle, and that's really just angling the wings upward as they leave the body of the plane. That puts the lifting surface up over where all the weight is, so if the plane rocks to one side, it just swings back to neutral. The other thing is up elevator, just bending the back of the wings upward just a little bit at the tail. So air will reflect off of that, push the tail down, which lifts the nose. Those two things will keep your airplane flying great. There's too little lift and too much drag on this plane. The ratios are just all off. Drag is the sum of all the air molecules resisting an object in motion. That's why windshields are now raked way back on automobiles. That's why airplanes have a pointy nose, to reduce drag. You want to cut down on the amount of drag so that it takes less energy to move forward. And with any flying machine, even our paper airplane, drag is one of the four main aerodynamic forces. The others are, of course, thrust, the energy that pushes an object forward, gravity, which is, of course, the force that pulls everything toward the Earth, and lift. That's the force that opposes gravity. And when all four of those forces are balanced, you have flight. The center of gravity, positioned near the center of the plane, to slice through the air molecules. It's very sturdy and flies very straight. The problem is, it can only fly about as far as you can chuck it before gravity takes over. But once you put some aerodynamic principles to the test, you can find clever ways to make the plane go farther. But what is lift exactly? For a long time, the Bernoulli principle was thought to explain lift. It states that within an enclosed flow of fluid, points of higher fluid speeds have less pressure than points of slower fluid speeds. Wings have a low pressure on top and faster moving air on top, so Bernoulli, right? Wrong. Bernoulli works within a pipe, an enclosed environment. Faster moving air in this case does not cause low pressure atop the wing. So what does? To understand that, we're going to have to take a really close look at how air moves around an object. There's something called the Coanda effect, which states that airflow will follow the shape of whatever it encounters. Let's look at a simple demonstration of these two things. As the air moves between the ping pong balls, it follows the shape of the ping pong balls and gets deflected outward. That outward shove pushes the ping pong balls together, inward. What we're talking about here is Newton's third law, equal and opposite reaction. So it's not Bernoulli that causes the ping pong balls to move together. It's that air being vectored outward, shoving the ping pong balls together inward. Let's see how that works on a real wing. Notice how the airflow over the wing ends up getting pushed downward at the back of the wing. That downward shove pushes the wing upward, and that is lift. So if the narrow wings on this dart aren't providing enough lift and the body of the plane is providing too much drag, what can we do? Well, we'll need to design a plane with bigger wings that slips through the air easily. Take a look at what's happening with the new design. With the center of gravity more forward on the plane, this plane will point nose down, allowing you to gain speed that's lost from drag. And then, when the plane gains enough speed, just enough air deflects off of these tiny bends at the back of the plane to push the tail down, which lifts the nose up. And that's how the plane achieves a balanced glide. What the bigger wing area does is allow for better wing loading. Since each plane is made out of the same paper, the weight is constant. The only thing that's really changing here is the size of the wings, and that's what's changing the wing loading. And a Reynolds number just measures kind of the size of a wing compared to the substance that the wing is traveling through. A Reynolds number helps scientists predict flow patterns in any given fluid system. And flow patterns can be laminar or they can be turbulent. Laminar flow is associated with low Reynolds numbers, and turbulent flow is associated with higher Reynolds numbers. Mathematically, a Reynolds number is the ratio of the inertial forces in the fluid to the viscous forces in the fluid. Reynolds numbers tell us the airflow may shift from turbulent at high speeds to more laminar flow at slower speeds. At launch, the flow is laminar only at the nose. Because of the Coanda effect, as the plane slows down, the air starts sticking farther and farther back on the wing. At slower speeds, the plane needs more dihedral to keep from wandering off course. This plane has more dihedral in the middle of the wing, where Coanda effect and Reynolds numbers have worked together to create smooth airflow. The center of gravity is forward, The up elevator lifts the nose, and now the glide ratio kicks in. This is Suzanne, and let's take a look at how this thing can really soar.